Good morning, people of physics, or good afternoon if you like to sleep in. Either way, it doesn't really matter. Glad you're here. It's week second to last. Oh my gosh, we're almost there, right? 4 days this week, 4 days next week. And the truth is, I'm going to quit giving you new material real soon. I'm going to throw out a few ideas this week. We're going to pull things together, and then we'll just about be done. So here's the goal. Today, we're going to think about the beginning steps of complex circuits. And there's not a lot to it, but I want to give you the basics. So you've learned about Ohm's law a little bit, and we've started to recognize that voltage is current times resistance. Let me just remind you what we mean by those things. Voltage is a cool idea because we're thinking about the amount of energy per charge. Yeah. So voltage is energy per charge. And that's kind of a neat thing to think about. If we look at a circuit and you have a battery and a bulb, here's a battery and a bulb in a really simple circuit like this. What we know is that the battery provides the energy, right? The battery provides the energy. Let's say it's a, 3-volt battery. And that current flows from the battery through the bulb and back. And the current that flows, I'm going to use the letter I for current, carries with it energy. Yeah. And in the bulb, of course, that energy turns into light and heat. And then the charge comes back to the battery and comes back empty and gets filled up. So at this point, the charge has 3 joules per coulomb, because that's the same as 3 volts. But then that energy goes away in the bulb, and when we get back, we're at roughly 0 joules per coulomb. So the whole process then repeats itself. Of course, the battery takes the charge, fills it up with energy again, it goes around, it dumps off the energy, and this process just goes over and over again. So when I mean complex circuits, all I mean is, what if we had multiple resistors or multiple bulbs at the same circuit? So we're going to look at what's called a series circuit for a couple minutes. And series just means in a row. So a series circuit is simply a collection of things where the current goes down a single path and comes back around. So that right there is a really simple series circuit. Those squiggly lines represent resistors. I mean, technically bulbs are resistors, but that's what a series circuit would look like. And we might call this resistor 1, resistor 2, resistor 3, and then our battery over here that has some voltage. And the neat idea is this. If the battery provides a voltage, let's say 9 volts, and these resistors all happen to be the same, the idea is kind of like we said before. As the current flows through the circuit, again, I'm drawing positive current flow here because I'm going from plus to minus. Some of that energy is lost out resistor 1, some of that energy out resistor 2, some of that energy out resistor 3, until we're back to the end and we're back at 0. So it's much like a single light bulb. The catch is that, well, if we have multiple things in the circuit, each one of them uses some of the energy. Now, to make this real nice, let's choose the 3 resistors to be the same. And if that's the case, then each resistor is going to dump off some of the energy. Now, you notice I'm using the term voltage and energy almost interchangeably, which is slightly dangerous, but it works okay. I've got 9 volts of energy per charge available, and I dump off 3 volts, which is really 3 joules of energy per charge at each resistor. And by the time I'm done, it's all used up, right? So here's a neat idea. If we think about this, what you've maybe noticed is that the total voltage provided is equal to the sum of the voltages. Holy cow, what was that? Hold on, let's do a little bit of quick analysis here. So you may have noticed that the voltage total, 9 volts, is equal to the voltage at resistor 1 plus the voltage at resistor 2 plus the voltage at resistor 3. You know what's really going on there is actually just an energy conservation statement. It says all the energy we start with ends up going to those 3 places. But here's a neat thing. We also know Ohm's law, right? We know, and you probably, like I started off with today, know that V is IR. So if we replace V total with I total, that's what the T stands for, and R total, we can do the same thing with each of these, right? V, oops, that's not right. we replace V with IR. So this is IR for number 1, and this is IR for number 2, and this is IR for number 3. And we're like, hey, exact same statement. Doesn't look as pretty because, of course, now it's a bunch more letters, but it's kind of neat. And what you'll notice is that as you go around this path, well, there is only one path. And one path is really the definition of a series circuit. Hey, if there's only one path, what does that tell you about the current everywhere? Well, it tells us that the current at any one place, whether it's in bulb 1, 2, or 3, the current at any one of those places have to be the same because there's only one path. In other words, all the currents over here everywhere are the same because there's only one path. So if all these I's are the same, well, look what we can do. We can just divide everything by I, and away they go. And look what we're left with. The I's go away because they cancel because they're all the same. And we're left with this cool statement that says the total resistance in the circuit is the resistance at the first one plus the second one plus the third one. Now, what really matters is this result. You can ignore everything I did with math to get here until now if you want. But the simple concept is this. If you have multiple resistors added together or put together in series, the total resistance is just what you get when you add them together. It's kind of cool. It's kind of neat. Let's take a look at an example. Hey, here's a circuit. I made it. Let's turn on the switch. You got 3 bulbs. Those bulbs are all the same. I've set them up so those bulbs are 1 ohm. By the way, did you notice if you click on the bulbs, it'll tell you their resistance? And I've set up the battery to be 9 volts. So my question for you is this. Well, what if we take the voltmeter and we stick it over here across all 3 bulbs? What should we see? Well, boom, we see 9 volts. But if we measure just across one of the bulbs, hey, we only get 3 volts on one bulb. Of course, if we measure across 2 bulbs, we get 6 volts. And again, 3 bulbs, we get 9 volts. Or if we measure any one of the bulbs, we get 3 volts. So the point is each bulb has a voltage drop of 3 volts, and together they combine to be the voltage drop of 9 volts, which of course you can see is the same as what the battery provides in the first place. And you'll also notice the current flow, it's the same everywhere. And it's the same everywhere because there's only one path. If we were in the lab, of course, I'd ask you to explore this and measure this and set up circuits and take a pile of data. But bottom line, that's what you're going to see. One path, series circuit, same current everywhere. And the neat thing about that, of course, is that the result is this nifty tool. What I want you to do today is give section 14.1 a read. Try the problem set that I attached. It's pretty straightforward. It's just a review sheet. And really the key is to get comfortable with the ideas in the section. This section simply talks about those ideas a little bit in terms of series circuits, the things we just talked through. But I think you'll find it's real quick. I'll do the same tomorrow with a concept called parallel circuits, and that'll be the key content for the week. And then we'll wrap it up. Have an awesome day. Drop in if you want to see me at this morning during office hours. Thanks.